Hi, everyone. Thank you for joining us today for the final NVM Express webcast of 2020. Today, attendees will learn how smart storage adapters are leveraging NVMe and NVMeoF technologies to offload servers from heavy storage tasks and are paving the way toward a fully composable infrastructure. Today's presenter is Jean-Francois Marie, Chief Solution Architect at Calray and Board of Director member of SNIA EMEA. Jean-Francois has more than 30 years of experience in the high-tech industry with various roles at Sun Microsystems, ENC Squared, and NetApp. Jean-Francois, thank you for offering your time today. We will let you kick off your presentation now.
Thank you so much for having me on this call. I appreciate the time here. Thank you for that last call and all the activities. So, you know a bit about me. Let me introduce Calray, perhaps. You don't know this company. It's been interesting what's happening here. So Calray is a French startup. Calray is designing processors, this new type of generation processor, and I will explain what it is about very briefly. We have been a startup for more than 10 years, and we are developing several solutions with big investors in Europe, right? We are based in France, and we have a global coverage. We have more than 30 patents because we are developing our own processor. We are developing our own compilers and libraries, as well as our own cards, and obviously our storage solutions, right? We address two markets, data center with storage and networking, and the embedded market with embedded cards and compute, right? So this is about Calray. Let's move forward into the subject I would love to cover today. I've been in this industry for more than 30 years, right? When I got started in the storage industry, it was about spinning drives, delivering like tens of IOPS per drive, right? SCSI connected or other type of connectivity at that time, right? When it was a mainframe type of connectivity. What I see now with NVMe and, for the past 4 to 5 years, something very interesting, like really a breaking through technology you want to live once in your career. And I see really NVMe being part of those breaking through technology. And I'm going to try to explain why, what is my perception about it, what are the evidence of the market, and I will go through some use cases I've been through as we develop those technologies as well, and how we use and leverage NVMe and NVMeoF technologies. So first, you may have seen that, right? This is not specific to me or to my company, but we see that in this data-centric era, there are many trends, right? Many things happening, many things changing the world, right? Obviously, you know the cloud revolution, right? You need to embrace the cloud to do things. The other thing is, when it comes about data management, it's interesting to see that many things are happening or are changing the game. First, network traffic is exploding, right? You may think about 5G, and 5G is not just about, the number, but it's going to drive massive change in terms of numbers, the number of devices being connected, the variety of those devices being connected. So thus, the different data formats being sent to data centers for analysis, right? Attached to that, this is only one example, right? Obviously, AI and all those algorithms to search and analyze data will make data capacity explode because, and I had many discussions with customers in the past years about, where to start when it comes to do something with data. What is important is not data per se, right? We used to say data is a new oil. So it's really raw something. You need to do something about it to get something relevant for your company, for your business or whatsoever, right? So you need to analyze more and more data to get something out of it. So you need to store more, to filter more, to analyze more. So it's going to put pressure on how you collect your data. It's going to put pressure on where you store your data. and it's going to put pressure on how you compute your data, right? Obviously, attached to that and linked to that as well is really security, right? This data is not located in the data center. It comes from everywhere. Any single device, for instance, it generates data. Everyone is connected, right? So how do you make sure the full chain is completely connected? So it puts pressure on, multi-tenancy, security, etc. So it's very, very complex. The chain becomes more and more complex. What we have seen is the traditional CPUs, right? AMD, x86, Intel x86, ARM, etc. Those multi-purpose CPUs are not enough. There was a promise in the past that generic purpose computers managed by software-defined stacks were the promised lands for tomorrow. It is not true anymore, right? You need an acceleration. You need something new because of that inefficiency. And inefficiency could be measured in several ways. And I think if you have concern about the planet, about ecology, about power, about human print on the planet, right? Power is certainly the most important thing. You may do everything you want with all the computers you have, but the power consumption will increase dramatically. And I've seen many data centers in the world where you don't have enough electricity power to power them all, right? So this is really a concern, right? It's not just about having all the components together, but how much those components are efficient. So we need to embrace something different. And that something different is that new type of processing accelerator, which are data-centric, right? They have to be built from the ground up to crunch data very efficiently with all the type of things, accelerating network, accelerating security, accelerating that data analysis, right? This is really key because those new type of processors make the things very efficient. And we see that coming very deep, and you have seen many of those coming on the market, and this is very important to be considered. Let's see with some examples why it's important. I've given some, right, but if we focus a bit more about architecture, data center architectures, applications, how do we see that, right? You may be familiar with HCI architectures. And the premise of HCI, I'm coming from the traditional SAN architecture. 30 years ago, 20 years ago, customer used to say, hey, I'm going to choose the best server, I'm going to choose the best network, I'm going to choose the best storage array, the best file system, the best application, and I'm going to build my Lego. And this is going to be my IT, my best of breed IT, right? This drives complexity. Perhaps some of you remember the nightmare of the interoperability matrices, right? You cannot manage, you need to manage the drivers, the HBAs, etc. So some years ago, like less than 10 years ago, HCI came and this initiative came and said, hey, yeah, let's go with generic purpose components, servers with drives and network and compute, and let's drive the things with software defined. Very easy to manage. No nightmare to build a Lego, just good enough, right? And have all the power in software defined. And there are clear limits with that, right? It's not just about reducing costs, but the promise of increasing agility and scalability is not right because those HCI clusters are quite limited in terms of the number of nodes you put together and in terms of the agility, and I will come back on that, right? What came after that was disaggregation, right? Trying to break that model into smaller pieces where you start to separate compute power and storage power and network power, right? You're still in that model of simple management, ease of automation, some kind of scalability, and this is basically what has been called HCI 2.0, right? You have seen some of those offerings coming on the market with some kind of separation. This has been good try. I'm not sure this has been widely used because HCI is so simple to be used, and customers have made trade-off, right? They have preferred simplicity and versus scalability, security, but there are costs to that, right? And what's happening with all the trends I've mentioned is you need something different. You need that new model. There is also a new trend coming, which is composable architectures. The dream of those composable architectures are, again, this Lego, but a managed Lego. So it's a fabric, it's fabric oriented, right? You have components connected through a network. So CPU, DPU, GPUs, memories, capacities, networks, and you assemble them and you build on demand the compute or the computer you expect to have based on your request, on your application needs, right? So really on the magic word is on demand, right? Obviously, we are just at the beginning of those composable architectures because you need to build all the different pieces together. But there are great technology already existing, and NVMeoF, NVMe and NVMeoF are definitively those good components to get started with composability. And what is important when we mention HCI 1.0, 2.0, we know that it puts those activities, data analysis, high network, etc., put a lot of load on the HCI cluster, put a lot of load on the interconnect. Many customers want performance. They use direct access to the resources, bypassing the hypervisors because it's not powerful enough, right? So they break the model. They break the agility because it's tied to the hardware resources. And when you embrace HCI or virtualization, you don't want to be tied to hardware resources. But if you want performance, you need to be tied to hardware resources. So the model is not very stable here, even if widely dispersed and used by customers. However, I think the other component is how you grow those infrastructures. It's well known that when you embrace HCI architecture, you have to grow compute, storage, and network at the same pace. All in one, the same model. HCI clusters are built on only one model. You put them together. If one model, if one node has not enough power, you need to add another node, right, with compute and storage all together. So it's a way you have those islands connected together. That's why HCI 2.0 tried to solve the problem, but it's still x86 based, right? All those solutions are still x86 based, so not very efficient versus all the criteria I mentioned before. So this is important to understand that there's an evolution here, and we will see in the next slide why NVMe is pushing those boundaries, right? So you have models widely used with a promise of software-defined is solving everything, but with the pressure coming from the data models, the number of devices connected, etc., this cannot work anymore. So they are game changers. If we look from a storage array perspective, what the industry start to call fabric bunch of flash. We do not call that JBoF, right? Just a bunch of flash, because just a bunch of flash does not indicate that your array is fabric attached. It could be SCSI attached, right? It could be PCIe attached, or it could be Ethernet attached or fiber channel attached. And FBoF is fabric attached to a fabric, right? And the protocol of choice today is NVMeoF. to drive this change. So what's happening here on this storage array side? I explained that very quickly at the beginning. I've been in this industry for quite a while, and at that time, if you remember, like 20 years ago, HDDs, the most powerful HDDs running 15K RPM, were delivering 300 IOPS, 300 IOPS, right? I don't know if you remember that, but at that time, there was a big pressure on drives. The demand from an application perspective in terms of response time were in milliseconds, and drives had tens of millisecond response time. So you understand that the application were demanding more than the drive could provide. So at that time, there were a big pressure on drives. So what happened at that time in the middle storage vendors, and you know them, you know, those big iron arrays, what they did, they developed big cache, made of memory, persistent memory, cached memory, battery protected memory, so that the latency provided by the storage structure is aligned to the demanding latency from an application perspective, right? However, I remember many discussions with customers where we had not enough drive to sustain that load, right? But at that time, like 20 years plus, pressure was on drive. Then what happened like nearly 10 years ago? Flash raised. First SSD to come. New companies like Pure Storage coming, reinventing the wheel in terms of how to handle IOs and how to treat SSDs. And those first SAS SSD were delivering tens of thousands of IOPS, right? So very interesting. We were moving at that time from 300 IOPS to 10K, 30K IOPS. So what happens is the pressure started to move from the drive to the storage nodes. All the storage appliances, and I was NetApp at that time, right, had to reinvent themselves because the industry moved from a rotating drive to a memory drive. So no more pressure on the spindle, just pressure on electronics, but fast enough to have to rewrite your IO drivers to take benefit of those new devices. However, the protocol between the storage node and the device were still SAS and SCSI, so not parallel, still serial attached, right? So quite a bit limiting, even if a SAS protocol is really powerful, but strong enough to put pressure on those storage nodes and to push the storage vendor to reinvent themselves and rewrite parts of their IO stack to manage those SSDs, right? So pressure start to move up from the drives to the storage node. Then next move, SSDs started to speed up. New type of technologies, and when I see SAS SSDs today, the latest generation, one drive can easily sustain 300K IOPS. So it's a 1,000x factor versus spindle, versus drives. This is massive, right? But it's still SAS driven, right? What's happening with NVMe? NVMe is providing a highway, massively parallel highway from the drives to the application through the storage nodes. And it's something massive happening, changing completely the game. And the jump is massive as well, right? So remember those numbers. SAS SSDs first generation 10K, replacing HDD 300 IOPS. Latest generation SAS SSDs are around 300K. What I see now with those Gen 3 PCIe NVMe SSDs, right? So NVMe attached directly on the PCI. We have about 500,000 IOPS per drive. And the latest generation SSD leveraging NVMe 1.4, PCIe 1.4, PCIe 4, sorry. I see drives coming with delivering 1.5 million IOPS. This is really great. This is really a very high bandwidth, right? It's like, I know the first generation NVMe SSD using French highways, 4 lanes, and now I'm using we are using US highways with 8 or 10 lanes at the same time, right? Nothing to be compared. So the pressure is moving up the stack, and we see that the massive change needed to be done in this industry to really take benefit of that I/O stack from the application to the drive directly. One good example are GPUs, right? If you take a GPU today, you need to feed that GPU because of the high power. So if you do machine learning or deep learning, you're using those training or inference algorithm, they will demand a huge amount of data, and they will ask to access directly the drive, bypassing all the stacks. And we see those initiatives coming, right? So this puts pressure, and this is why it's disturbing on the industry, because the full I/O stack has to be rethought. All the storage node OS has to be rewritten, because no one of them can handle this massive load coming from the drives. This is really a massive disruption in the industry. So this is really that move from SCSI to NVMe, 1 queue, 256 commands versus 64K queues and 64K commands, right? This is really the time of massively parallel I/O. And you can understand now that only processors that have been designed to sustain those massively parallel streams can handle that type of I/O. And I see the comparison every day. In my company, we don't speak 10K I/O, we don't speak 100K I/O. Our reference is million IOPS, always million IOPS. And the latency is not a matter of milliseconds, we're speaking microseconds. This is really our nightmare every day. We have to handle solutions to deliver million IOPS while having a latency below in tens of microseconds. So the change is massive. So in the industry, we see that very clearly. Obviously, you see that from an NVMe perspective, from a drive perspective, but we see that also from a fabric perspective. And you need to have a fabric or an interconnect that has this ability to transfer the power of those next generation SSD directly to the compute nodes. And NVMe over fabric has been designed for that, right? So either it's NVMe, TCP, or Rocky, or Fibre channel. Those massively parallel algorithms have embraced NVMe to replace SCSI to handle those massive parallel streams. And that's where, and that's very funny, because what's happening on the market is exactly what happened some years ago when Fibre channel raised. The promise was to have shared storage for better utilization, for better provisioning, for better sharing, replacing internal drives. And this is exactly what's happening. The promise was HCI with internal drives, but NVMe drives in those HCI is pushing the boundaries for applications of the applications, right? And what we see here is NVMeoF, is providing an alternative to those internal drives, because it has the power, it has the bandwidth, it has the right latency compared to those internal drives. So we see a massive change here And the adoption is starting to ramp up slowly but surely to embrace those new technology. And I can tell you, this is really major and stable, right? We run daily tests, and we don't see any problem using those protocols. To give you a perspective, because that's also something interesting. If you're familiar with storage nodes, storage appliance, usually what you see is an array with two controllers. Years of engineering to design those red controllers, active-active or active-passive with two controllers, driving those SAS drives or SCSI drives or SATA drives or NVMe drives. Now the industry is embracing really a new model. It's a generic chassis with good enough PCIe bandwidth and lanes, right? With some PCIe slots, and the intelligence will be managed by cards. You're going to plug in those PCIe slots, and you have some vendors already providing some great solution to handle IWAP, RoCE, TCP, Fibre channel in those new generation arrays, right? And what we see, and you see the numbers and some specs here about what could be, the ideal model on the market. You see the number of IOPS, the bandwidth. This is really impressive compared to any single SAS array of that kind, right? Take a NVMe chassis using Fibre channel. You don't get those speed. You get 2 million IOPS. You get like 20 gigabytes per second, but you don't get those big numbers. So this is where the revolution is coming. This is how this is going to change the game in the industry landscape. Obviously, you need application to consume those workloads, those massively parallel threads. Containers are interesting because they are massively parallel by design. So it seems as a good combination between using containers and NVMe technologies or NVMeoF technology, right? So really a interesting move here in terms of how storage arrays are designed. So really a new type of things. So this is the first use case I had to explore, right? Is how NVMe and NVMeoF are changing the way storage arrays are designed. And I think this is following another big trend in industry is to use very simple components, assemble them to get a solution to solve customer problems. What we see also is the use of standards more and more. We talk about NVMe and NVMeoF, right? What I see as well in this industry is the power of communities, the power of shared codes. Many users are embracing the sharing of those codes and porting to their platform. And one good example of that is SPDK, right? The Storage Performance Development Kit. It's really powerful, completely open. Anyone can add his own libraries. So the value is not on proprietary code. The value is on how you assemble those things together to solve customer problems. And that's another big shift in the industry. Let's continue and let's try to explore another utilization of those breaking through technologies. And I would love to look into more details about disaggregated composable infrastructures as an alternative to HCI. I mentioned that at the beginning, but let me give you a very detailed example on how to use those technologies. On the top of it, you're familiar with standard HCI, siloed approach, managed with software on the top of it, with a promise to replace years of storage expertise to make things very simple. Yes, things are simple. Yes, it's running well, but it's really limited in terms of scalability. And I will explain more into the details when it comes to the presentation. What we propose here with leveraging NVMeoF and shared storage is a move to use smart storage adapters in those nodes so that you build a shared repository, preventing or allowing all those nodes to access the data the same way as if the data would have been local, right? That's very important. So really it's the idea of providing, based on really standard components, a global repository to offload completely the storage services from the x86. And we have seen that storage services may take up to 30% of x86 load. If you consider that, knowing that the license you pay for applications is certainly based on number of cores you use, the more cores, the most costly is your license model, right? So the less core, the best for you, because your price for your application is going down. So here the idea is to make sure that the x86 power is completely dedicated to applications and not to infrastructure. So this idea of disaggregation is to really offload those services, right? Scale out model, obviously, which is the model today in order to handle capacity and performance increase, and proposing an heterogeneous model so that you're not locked in with one model for your HCI cluster. So let's go into the details to see how things are happening. So this is an HCI cluster made of those nodes with your TCP/IP cluster interconnect. Quite common to run your application. You all know that. You know how it works. You put whatever software you want, whatever hypervisor you want on the top of that is going to be exactly the same. So what's happening? You create a VM, you get some data, you load your application. Very easy, right? Your data is local to your node. Your application is local to your node. This is running well. But real life application in a virtualized platform, so in a real situation, VMs are moving. They are not stick to one node. They move from one node to another. And there are several reasons for that. First one is my application needs more power. I don't have enough power on my node. I'm going to use an empty node or a more powerful node. And so I'm going to move my application to that node. Or my application needs more space. I need to move the whole thing to the node where I have more space because it's not a global shared repository, right? You have the illusion to have a global shared repository, but in terms of performance, it's not a global shared repository. So for one reason or the other, you're going to move your application or your VM. So what's happening? You create fragmentation. Your data is still located on node 1, while your application is running on nodes 5 here. Your application will access its data through the interconnect, and it puts pressure on the interconnect. And we all know that this interconnect, if it's not a dedicated 10 gig or 25 gig Ethernet link, it's a major risk for the infrastructure. So the whole cluster is based on that link stability and performance. So you create instability here just by moving your VM around, right? Obviously, what you want, okay, this is not good enough. I'm going to move my data as well, right? This is important. But before doing that, perhaps what you have experienced is you have created extra data for your VM. So depending the hypervisor you're running, what's happening is your data will be located on the node you're sitting on. So good enough, right? So you have new data coming in, located exactly where your application is. So it's running well for that set, that data set, right? But however, your data is completely fragmented across the cluster. And this is only one move for the VM. You could have many moves across the cluster. So obviously, the admin of the system would love to reorganize things. Perhaps you never do that, right? You're happy with that because it's so complex to manage. But perhaps if you're clever enough, what you want to do is to remove your data. And what's happening again, depending on the amount of data you have to move inside the cluster, you put pressure on the interconnect. And this interconnect is managed by the x86, right? This is an x86 network stack. So you put pressure because of storage services, and you put pressure because of network activities on your x86 stack, and you have experienced that, right? This is impacting the full cluster. So what can you do? If we consider this cluster, what you can build very easily is leveraging NVMeoF. So you add a specific data network, right? So it could be TCP, it could be Rocky. You have several options here depending what hypervisor you're running. The premise of NVMeoF obviously is first to create a data network. So every data transfer, we'll see that, will not use the interconnect. And this is the first aim, really the first aim of this NVMeoF. Obviously, you can leverage NVMeoF storage arrays. So you're not obliged to use storage inside the nodes. You can mix nodes with capacity. You can with nodes without capacity. So the right-hand side node won't have drives in that, just the boot drive. And this compute node will take the capacity from the GBOF or the FBOF connected to that fabric. So you have this data fabric to share data across the nodes without putting pressure on the interconnect. Let's take the same example I've just taken before, all right? I'll create my app, create the data associated with that. Everything is doing well. I'm moving my application. What's happening? While I move my application, I still put some pressure on the x86 because all those stacks, NVMe stacks, storage stack, network stack, are still managed by the x86. I don't put pressure onto the TCP/IP interconnect, right? But still, I'm using it's better, but still using x86 stack to manage the different storage infrastructure, right? And you see the model, right? Moving the application, putting pressure, then moving the, sorry, I forgot to mention. I could do the same. Like if I need to move my data back to the node where the application sits, right? I'm going to put pressure on the x86. So this model is interesting because it does not use the TCP/IP stack, right? The cluster interconnect, but still it's using the x86 power. So still limiting the power of the I/O and the movement you can have, the freedom you can have with that infrastructure. So what we do with those smart adapters, we leverage obviously NVMe and NVMeoF, and we offload completely the storage stack. So in the model I explained here, creating my app, which is data, if I move my application, there's no pressure on anything. I don't use the TCP/IP interconnect. I don't use the x86 cycles, no impact at all. So I can freely move my application around. And the good news is, because I have this dedicated data network building a global repository, I don't need to move my data. I can have my data wherever I want in the cluster. The application will access that data set as if the data were local. That's very efficient. So you gain cycles. You gain cycles in terms of administration. You gain cycles in terms of x86 load and TCP/IP load on the cluster. So your cluster is far more stable. You can have more nodes on your cluster. And the beauty out of it is also you can take benefit of those external storage providing NVMeoF, right, to expand capacity. So it's really that new model of HCI where you have nodes made of storage and compute. You have node made of just compute, and you have node without compute, but the storage. You can mix and match all those things together, building the next generation composable architectures. In order to do that, we need to explore a very nice piece of technology, actually two of them, PCIe, peer-to-peer, and NVMe emulation. And that's interesting because when you think about adding a card in a server, you're going to tell me, oh, I need a driver for that card. How do you manage those devices, right? It's going to be complex. I need a driver for this hypervisor, for this OS, etc. How do I access those resources? And this is explained here in the slide coming. First, so when I add a card into a server, this card needs to be an endpoint from a PCI perspective. So x86 will be the root complex of the PCI bus, will control the devices, etc. That's where the challenge is. If I want to take control of the drives, I need to bypass the x86, or I need to tell the x86, hey, please, you're not the master anymore. I'm going to take control. That's where you have peer-to-peer. PCIe peer-to-peer is a piece of technology that allows you to do such, right? So the card inserted in the chassis, in the server itself, will manage, enumerate the drive, offloading completely the x86 from that control. Very interesting piece of thing here, right? That's the key of the solution with that peer-to-peer, completely standard technology. So you need to be endpoint. You need to be connected on the same PCI of the x86 thing, root complex, and you take control of those devices. What we see here are two types of drives, NVMe drives or SAS drives. Many of the HCI installation or compute node installation are using SAS drives. The next generation, and we see that raising a lot, right, are using NVMe drives. But we all know that the pressure of those NVMe drives will be very high, right? So you need something to help there. I'm seeing the question. I will try to answer. Requiring a parallel NVMe architecture. Yes, you need that parallel architecture to handle NVMe and to be completely separated from your TCP/IP stack, because you need to separate things, right? The TCP/IP stack in this model is still managed by the x86. If you want to offload the TCP/IP stack, you would need a smart NIC. This is exactly the same model. Here, the card is just handling storage activity, right? If you want to offload the TCP/IP stack, you would need another card or the same card doing both storage and networking. And this is another exploration as well in our project roadmap, and to offload this TCP/IP network, right? So here it's about really the storage and NVMeoF. I hope it answers the question. Please tell me if not. So what you see here are also those SAS drives. And smart cards has this ability not only to manage NVMe drives, but they can also handle SAS drives. So they can fit in any chassis. But now the question is, okay, I understand how to control the drives. Now the question is, how do my application stack connect with that card? Do I need a driver? So this is where we have a new piece of technology coming with NVMe, which is called NVMe Emulation. So NVMe Emulation is a piece of technology that allows the card to be seen as an NVMe device. So from a host perspective, from an x86 perspective or application perspective, the only thing you need is an NVMe driver. You don't need a specific card driver, because the card will enumerate other drives and present them as NVMe devices. So interesting, even the SAS drives will be seen as NVMe devices. Right? You just need an NVMe device. So the card will offload completely the control of the drive, will publish internally the drives as NVMe drives or NVMe resources. And because it's also an NVMe offloading engine, it's going to publish all the drive over NVMeoF. So the internal drives will be seen, this component here, this server plus drive will be seen as a storage array from an outside perspective. So you can easily connect any initiator supporting NVMeoF to access those drives as if this system would have been a storage array. So if you look at the data flows coming in and out, from a SAS perspective, obviously, the card will speak directly with the SAS HBAs. If you have a SAS red controller, that's fine as well. You just see those LUNs, those SAS LUNs published on the PCI switch. Obviously, you need those, right? Because SAS drives do not speak PCI. You need that component in the middle that is making the translation between PCI and SAS. While for NVMe drives, they speak natively PCI. They are directly connected on the PCI. So the card is accessing those directly through the PCI switch or bus, right? So this is important to understand that for the SAS drives, you're going to go through those SAS HBAs or SAS red controllers in order to get access to the drives. And what's happening here, you completely offload the load, right? Completely offload. So if you want to run, if you have a SAS HBA running red, obviously you don't need red being handled by the smart adapter. But if you have just devices without data protection, the good thing about those smart adapter is they can handle a very efficient calculation in order to do error decoding. So that's easy because you don't ask the x86 stack to take into account data protection. This is going to be handled as well by the card, right? When it comes to NVMe activities, obviously any request coming in and out from the NVMeoF going through those NVMe drives will go directly on the PCI bus, bypassing, obviously, as I said, the x86, and the x86 will access using the NVMe driver, as I said. I have a question here. Is the card presenting a new namespace to the x86 NVMe? Yes, you will get an NVMe namespace, right? So exactly like a new NVMe device. And you're going to access this NVMe and namespace. So if the card is in pass-through mode, let's say you have 6 NVMe drives in your chassis, the card will enumerate those 6 drives and will propose them as 6 new NVMe drives, new namespaces to the x86, right? So the x86 will not see the physical drives, but we'll see that layer in the middle using NVMe emulation. But now, if the card is, let's say you take those same 6 drives and you create a ratio coding like a 4+2 type of scheme, you can only present one slice of those drives or the full capacity. So the new virtual namespace you're going to propose will be made of those 6 physical namespaces, right? As only one big namespace. So yes, it's providing a completely standard NVMe namespace. The other question is that do this solution require a parallel NVMe architecture that is connected together? I'm not sure I understand that question here. You don't need a specific parallel NVMe architecture. It's just completely standard architecture. You take a standard server with PCI slots in which you have NVMe drives. You connect the card and you just use them as just an NVMe resource or PCIe resources, right? But those, on the top of PCIe, you have NVMe. So if you're not familiar with that, right, NVMe is a new command replacing SCSI. and it takes benefit of several transport protocol, and PCIe is one of them. NVMeoF, OF using TCP, RoCE, or Fibre channel, or others, right? But NVMe is really the command replacing SCSI. So you don't need a specific parallel NVMe. You just use what has been defined with a standard and what you can find in any chassis today, right? So no need of specific things. Just use the components you have. I hope this answers the question as well. In conclusion, what we see here, that big change in the industry, again, I said, and the challenge we see, because more and more compute node will use NVMe SSDs. And the challenge of those new fabrics, led by the use of NVMe of a fabric protocols, is to make sure that we provide application the power to exploit the full power of those new NVMe SSD. And this is really a challenge, right? I know many data centers that can fit in only one drive. I've been working for many customers whom have less than 100K IOPS. And what I'm saying, one drive we're going to handle 1 million IOPS is 10 times more that I need. How do you handle that, right? So we need to make sure that for customers, those technologies are of the right use. They're gonna benefit it for their application and for their business. The second thing is, as you understand, is x86 cannot handle those. They can't handle both applications plus this massive pressure coming from NVMe devices. I've discussed with many partners and customers, and they see the time today where you need offload engines. Offload engines for the network, named as SmartNIC, but offload engine for the compute, accelerator cards, and offload engines for storage as well. Right? You may find combination of SmartNIC because the word has been, let's say, used by different vendors. Say, hey, a SmartNIC is this, or a SmartNIC is this. Smart means you put intelligence in something. NIC means network. So it's adding services on network. Smart storage adapters are taking care of storage services and do not mix them. It's not the same. Handling NIC, handling network, TLS, encryption is not at all the same as handling storage services. And we see the convergence of those two for those super powerful DPU to be able to handle network acceleration as well as storage acceleration at the same time. This is also proposing those new type of composable disaggregated architectures, because finally the server plus the storage, the devices, the nodes, they don't care. You don't care what you choose. Just plug in the card and you can compose your nodes. Finally, we all know that to be efficient in terms of compute, you need to have the data very close to the compute. That's why HCI was super powerful, but now that's not enough. With that new model here, you don't care, because wherever your data sits in that fabric, you can access using your compute as if it was local. That's very efficient. So you have the freedom to build the computer you need with that fabric, because it proposes you the right latency and the right performance between the compute and the data, right? What we see also in the industry is a big trend for programmability, ease of use. Customers, they don't want to use dedicated resources. They want to have a component they can program using standards. I mentioned SPDK, right? This is very powerful. If you have a look at GitHub and SPDK deliveries, you're going to find many things, right? To take benefit of those new technologies, right? And you have the freedom to contribute and give more. So SPDK is one for storage, DPDK is another one, or ODP for network. Those open framework are of the promised land of more community driven innovation industry, and also fully programmable, right? It gives freedom to really design components which really are made for specific use at customers. And obviously, I'm really a big fan of standards, right? I'm completely against closed and proprietary infrastructure and protocols, and the industry is driving those standards. And here, NVMe and NVMeoF are definitively good ones, breaking through technologies, and it's important to embrace those. At least in my company, and I've seen many of those are embracing those standards, because this is for customers really the freedom of choice of the best components to solve their issues, right? Well, I think I'm done. A lot to cover. So I see some questions here.
Yes, Jean-Francois, thank you for answering some of those audience questions. We do have a couple more here if we'd like to wrap up with one or two more. One audience member would like to know, is the original NVMe SSD namespace going to be removed, or will that namespace still be available? How do you prevent the simultaneous access from P2P path and the direct x86 path?
So very good question. So with peer-to-peer, the x86 do not have access to the NVMe namespace. So the card is taking control of that namespace. Obviously, it's not a shared namespace where you have two devices accessing the namespace at the same time. So we replace the x86 access to the namespace with the card access to that namespace. So exactly, we take control, and the peer-to-peer is preventing access. So this is how the peer-to-peer is working. You take control. The other question is, does this require a switch to connect to the NVMe drive for peer-to-peer? No. Are you using the x86 root complex to facilitate the peer-to-peer transfer? So yes, obviously you need to communicate with the x86 root complex, right? Because it's still the master of the PCI. In terms of the PCI architecture, yes, you need a switch PCI, because you need the number of lanes, right? And it's very rare not to have a PCI switch in the middle of those x16 PCI bus architectures, right? So basically we see switches, there are many modes. It may work without, so peer-to-peer does not request switching, but we see more and more PCI switch on motherboards to propose those things, right? Because when we speak about those performance, we are speaking about PCI by 16. It's not PCI by 2 or by 4, right? Drives are by 2 or by 4. x86 is by 16 or more. Cards, usually smart cards, are by 16, because you need that power. You need to take the full benefit of the PCI, right? So obviously, to have all the things communicating all together, you would need those PCI switches on the motherboard. And it's going to accelerate, because I start to see by 8 SSDs or SSDs by 16, right, to provide even more than 2 million IOPS per drive. So yeah, the big things are happening on this matter as well.
Thank you, Jean-Francois.
My pleasure.
We really appreciate you offering your expertise today. If we didn't get to your question today, we will be releasing a post-webcast blog to address your unanswered questions. And this webcast has been recorded, and it will be published to the NVM Express YouTube channel within the next coming weeks. And we want to thank you all for joining us today. And on behalf of NVM Express, we wish you a relaxing holiday season and look forward to continuing our webcast program in 2021.
Thank you so much. Enjoy Christmas break.
Thank you. Bye-bye.
Bye-bye.